In nature, hydrogen is highly available in its pure form. Therefore, it has to be generated from something. It has to be produced from other sources, other chemical species. There are different ways to produce hydrogen. In fact, there is a whole rainbow of different options. These differ significantly in terms of the raw materials, the production method, and their sustainability. In this lesson, we look at conventional ways of producing hydrogen, the most popular one being the so-called steam reforming process, from which we get grey hydrogen. We will learn which aspects need to be taken into account when producing hydrogen via this route, and we will also find out about measures to clean up this relatively dirty process and to turn the formerly grey hydrogen into a blue one. In any case, various chemical engineering aspects need to be addressed. These are: which raw materials are used? How does the production process look like? Which chemical transformations take place? This goes hand in hand with the formation of byproducts and the question about emissions. And finally, which product purity can be achieved? Before we look at the technical basics of steam reforming, let us have a quick look at some numbers. The vast majority of all hydrogen that's produced today is still made from fossil fuels. Natural gas accounts for 62%. Coal, yielding the so-called black hydrogen, is responsible for 21%. And hydrogen is also formed as a byproduct, for instance at refineries and in the petrochemical industry. This sector accounts for 16%. This brings us very close to the total amount of production. In other words, very close to 100%. We will now look at grey hydrogen, making up for the highest proportion. That comes from natural gas, the chemical species methane. So, in order to obtain hydrogen from methane or any other hydrocarbon source, we need to split up this molecule. This is done by a process called steam reforming, or in the case of methane, steam methane reforming, SMR. This is the most common method to produce hydrogen, or more precisely, hydrogen carbon oxide mixtures. And it is not new at all. The process dates back to the 1920s. In this process, methane is catalytically converted through reaction with steam into hydrogen and carbon oxides, carbon monoxide and carbon dioxide. This requires an input of energy. Let us take a closer look at the underlying chemical reactions first. The main reaction, the reaction of methane and high-temperature steam to hydrogen and carbon monoxide, is always accompanied by the reaction of carbon monoxide and water to carbon dioxide and hydrogen. This reaction is called water-gas shift reaction. For this reason, carbon dioxide is obtained as a byproduct. Moreover, methane is only partially converted. This means that the product stream also contains unconverted methane and excess water. It is important that the reaction conditions, such as the temperature, the steam to methane ratio, and so forth, are precisely set in order to achieve high hydrogen yields and in order to prevent unwanted carbon deposition. The reforming reaction is a highly endothermic reaction, which is characterized by a positive standard enthalpy of reaction. It thus absorbs heat from its environment. Steam reforming is carried out in a number of parallel externally heated tubes, the so-called reformer tubes. Reformers are mostly top and wall-fired box-type units. For the reaction to proceed at a sufficient rate, steam reforming is generally carried out in the presence of a heterogeneous catalyst, which is filled in the reactor tubes. The catalytically active species is nickel, which is supported on a carrier material. This is generally alumina. In this context, all aspects of heterogeneous catalysis, such as catalyst composition, structure, catalyst activity and stability, as well as catalyst degradation and poisoning due to contamination must be taken into account. Overall, the whole process is somewhat more complex. The natural gas must first be purified, so it passes at least through a desulfurization stage. It is preheated and goes through a pre-reforming stage before it is fed into the actual reformer that operates at 800 to 900 degrees Celsius. What we then get is not pure hydrogen, but a hydrogen-rich synthesis gas, namely a mixture of hydrogen and carbon oxides. We may simply call it syngas. The benefits of steam reforming are pretty obvious. It is a well-developed, highly efficient process with efficiencies between 70 and 80% for large-scale hydrogen production. However, the product is synthesis gas, which means that further purification steps are necessary to get pure hydrogen. The real disadvantage is that it is based on fossil fuels. It is therefore associated with the formation of CO2, which, if not used further, is emitted into the atmosphere. Efforts are therefore being made to clean up this process, and this is where blue hydrogen comes into play. When we talk about blue hydrogen, still the same process is meant, but it is combined with carbon capture and storage or carbon capture and utilization. This means that we still make hydrogen from fossil fuels, but instead of letting CO2 escape into the atmosphere, we capture it and either store or use it. Let us now briefly summarize what we have just discussed. At present, hydrogen production is still based almost exclusively on fossil fuels. The majority of production, about 2/3, is based on steam reforming of methane. This gives the so-called grey hydrogen. In this process, methane is converted with steam and hydrogen and carbon oxides are formed. The efficiency is high and lies between 70 and 80%. However, carbon oxide emissions have to be dealt with as a hydrogen-rich syngas is obtained as product.